Hi everyone, and welcome to the talk on fair scientific formation, which I'm pleased to deliver as opening address of the 24th International Conference on Grey Literature. I'm Markus and I lead the Knowledge Infrastructures Research Group and co-lead the Open Research Knowledge Graph Initiative at TIB Leibniz Information Center for Science and Technology in Hanover, Germany. Imagine a world in which scientific information is not just buried into documents, but also organized in databases. How would we conduct research today? And what would this mean for modern knowledge societies, which are very much relying on scientific information, as we have seen during the last years of the COVID-19 pandemic, but also in other contexts of societal challenges like climate change? Scientific information is really a key source to advance knowledge societies in the right direction. During the last decades, we have seen a strong digitalization, meaning a transformative process towards information systems in many sectors of the economy. Some of you might remember mail order catalogs as they were sent around to homes. You could get informed about products, their characteristics, prices, and you could also, to some extent, compare products, maybe even across different catalogs. Today, this is not common anymore. Today, we use information systems like Amazon and other systems that have transformed, have had a digitalization of the original information printed in documents towards information systems that are now capable of enabling new services. Not just it's easier to search, you have different search functionality like faceted search, but also you can more automatically, for instance, compare information, products across vendors, the characteristics of mobile phones, for instance, not just price, but also memory and other characteristics. In similar manner, we used to print maps on paper, and I remember my parents having printed maps in the back seats of cars. And we use this approach to guide us from A to B on the hopefully shortest route. But today also we have moved away from printed printed maps towards digital services, information systems like Google Maps or OpenStreetMaps. And again, they have organized the information about the roads, but also integrate information for the weather or traffic congestion. And therefore, they are not just telling us or guiding us on the shortest route from A to B, but also on the fastest route, taking into consideration also weather conditions and street conditions. So this is a complete different approach to information management, and also that has enabled completely new services on top of this information, in contrast to how things were done a few decades ago. In research, we have not seen quite such a transformation. So we have had certainly a digitization in contrast to digitalization. Digitization is not a process of a transformative process towards information systems, but more like, okay, a scanning of the original printed documents, or a creation of documents in digital form, in natively digital formats, but not a moving away from the document-based communication. Indeed, it started several centuries ago with the first journals, as you can see here. Le Journal des Savants was probably one of the first scientific journals. And you know, for a few centuries went on in similar manner. We have published in text, and the papers haven't really changed that much. So they have a title, they have authors, they have publication date, and usually some abstract and some figures that used to be printed or created by hand, maybe even. And all this has, of course, moved into the digital space. So today we create this document in digital form natively, and we use a number of tools to create figures, tables, and so on, and other artifacts published in papers. So that there has been a transition, a digitization of these documents, but not really a transformative digitalization. So the information in these papers is still communicated in document form, and we don't really have a database that curates, manages, and exposes the information for applications in an information system manner. So scientific information is data. I think that's not controversial. And this data is not fair, certainly not for machines. So basically, when we go out and try to find scientific information, what we do find and what we do access are documents, which then we need to read to extract the information that we need. And machines, yes, they support us in finding documents, largely based on keyword-based search, but they don't help us very much in reusing the content, in comparing, for instance, the content, in giving us access to the data inside. So we don't really find access and scientific information, and the information inside is not really interoperable, often not even for machines, for humans, but certainly not for machines. And therefore, the reusability of this content, yes, for humans, we can read and extract, but it's very inefficient because of the lack of machine support. So let's look at this paper, this page here in more details. First paragraph has a sentence: IRE binding activity was significantly reduced in failing hearts. And it also points to a figure 1b, which I'm highlighting here. And this figure is basically a plot of data, and this data happened to be also in CSV format. And as you can see, once you encode this data in this form as a plot in image, it's useful for humans to quickly digest the data, but for machines, it's not really reusable because this data is now pixel data, and it's very difficult for machines to try to extract the actual values once it is in this format. Note also the p-value here is approximated to 0.001. That's also useful for humans because that's all they care, to see that there is a highly significant difference between these two means. But for machines and for usability, for instance, in systematic reviews, it would be much more useful to have the actual p-value. So this is what machines should really be consuming. So a machine should be consuming the information about the student's t-test, which was executed here. And the student's t-test should be typed by using a term of a particular ontology. And this is here the ontology for biomedical investigation, OBI, that has a term for student's t-test. A student's t-test has generally also a dependent variable. That would be here, in this case, the iron responsive element binding. Again, also here we can use an existing term of the gene ontology. A student's t-test has typically also a specified input. That would be the data used in the t-test. And again, here we can use a direct link to the DOI, using the DOI of the data set, so that we can give direct access to humans, but also in particular to machines, to consume then this machine readable data. which stands very much in contrast to the plot, which cannot be really read by machines. And the student's t-test has also specified output. That would be a p-value. Again, we use here a term of the ontology for biomedical investigations. The p-value has a scalar value specification, which here is the actual p-value. So not the approximated value 0.001, but the actual p-value that is computed. So Barr and Mons, a while ago, over 15 years, said in an article that scientific writing can be called information blurring. I think it's a very nice way to put it, because we have information that we produce during the research life cycle, often in structured manner, or we have the product or the source data in structured manner used in data analysis, for instance. And then we bury this in products like visualizations and try to then mine it again. And of course, this is very expensive to do, because you have to train models to do so, or algorithms, and it's also highly inaccurate. Teresa Atwood and colleagues a few years later noted in a paper that we have essentially failed to organize information in rigorous ways, so that finding what we want and understanding what's already known today becomes increasingly costly as an experience. So this is the inefficiency of extraction from text that brings that cost. And Julian Higgins and colleagues in the Cochrane training handbook, which, as you might know, Cochrane focuses on extraction of information from clinical trials, about clinical trials in the life sciences. They have this problem as well, that they would like to build databases with this information. And note that this is largely a manual process. So there has been, of course, developments in machine learning in recent decades, but this kind of data extraction from documents is still a manual process, and therefore very expensive to do. Still, it is no longer the 17th century, of course, and many things have happened, in particular at the level of metadata. So the research infrastructures, colleague communication infrastructures have agreed on certain metadata standards, and also agreed on mechanisms to interlink metadata about artifacts, so articles, data sets, but also authors and organizations, which are often increasingly also persistent identified, these entities, and described with standardized metadata and interlinked. So that's great, because given any of these entities, you can basically traverse this graph, called also the PIT graph, and discover assets and entities that are related. And for this, there are, of course, also a number of systems that manage this metadata, like Eurocris, the research information systems, Vivo as an open source, Pure from Elsevier, and also graph technology have been used increasingly. There are a number of projects. The Australian Research Graph, or OpenAir has a research graph as well, and also Springer Nature has the so-called SciGraph, which builds on this kind of graph technologies as a database. So that's interesting and certainly useful, because it organizes the metadata around articles, their linking to data sets, and organizations and people, instruments, and artifacts relevant to the context of a research investigation. But it doesn't really capture, the system don't really capture the actual content, the actual scientific information in articles. So that content, the scientific information, remains not really accessible and reusable for machines. That said, there are many communities that have identified that problem and also created efforts, often in the context of systematic reviews. They have executed this task of extracting information from literature, from a corpus, generally very limited, of course, because they are focused on a particular problem in a specific domain. And then some of these communities have made this available, this data available to reuse, and so they have a service where you can download it, and maybe they have also developed some kind of visualization of the data so that they can enable analytics on top of this very highly specific, domain-specific data. So there are good examples, for instance, in biodiversity, so high-knowledge.org is a good example. In invasion biology, they have extracted information about hypotheses in invasion biology and their support or questioning in the literature and their relationships. So you can look at these networks of hypotheses in invasion biology in a visual manner. Platzi is another well-known example in the biodiversity domain. The Cooperation Data Bank is an example in social science. You can see here they have about 2,000 papers with extracted information about participants and a number of effects and studies. And they built also a visualization on top of the data for this data to support analytics. And the air quality data collection effort at Forschungszentrum Jülich, in particular in the context of the COVID-19 pandemic, is another good example. They have here about 150 publications with 1,000 measurements that they extracted from the literature and created a database, which again powers some analytics. Papers with Code is another good example in machine learning, where they extract standard metrics for certain tasks like object detection, which communities have developed algorithms and models to detect objects using some benchmarks. And then you can basically also show who is the leading algorithm today and how is the trend of the performance of various models over time. So you can see how the community trends for a particular task in machine learning. MetaLab is yet another example in the cognitive development research. I'm sure that there are many more that I'm not listing here, but I hope you get the sense that there are a number of communities that, of course, extract information for their own purposes from the literature and try to organize this information. And the Open Research Knowledge Graph is yet another service which has in principle the same issue at heart and aims to scale this problem and solutions for this problem beyond a particular domain and beyond a particular research question and make it more generic as a platform. So the benefits, I think, are obvious, right? Once we have a database with structured information, we can, for instance, compare scientific information across the literature. You can think of this like Amazon product comparisons just for scientific information. We have here, for the case of SARS-CoV-2, basic reproduction number estimates across the papers here in the columns. You can capture the main information, of course, the basic reproduction number estimate. Here that has value 3.1 in the first paper. And then information about, for instance, where the study was conducted and the time period, so that you can start not just comparing across the literature, how the value, the basic reproduction number in this case, behaves, but also made some regional studies. Is there a difference between regions? So given this data, you can then start also integrating data from a number of comparisons. For instance, for a case fatality rate, you can draw a mean, and as well as for average basic reproduction number, and then you can plot SARS-CoV-2 on such a map of infectious diseases and see its deadliness and contagiousness relative to other infectious diseases. And creating such products, once you have the data in a system like ORKG extracted from the literature, is relatively easy. So, for instance, by simply supporting the integration of a system like ORKG with a computational environment, which then allows to simply read this comparison data into a data frame. And so it allows you to reuse this data very efficiently. Another thing that you can do is integrate ORKG with the existing scholarly communication infrastructure here, for instance, DataSite Commons, which is built on top of the PIT graph. So you can see, you can discover these kind of comparisons as artifacts, as published artifacts also in DataSite Commons by looking up their DOI. So we allow for persistent identification of these artifacts in the ORKG, and then you can discover these assets across the scholarly communication infrastructure. And of course, we also relate the underlying literature that was used in this comparison here for, again, for the basic reproduction number. And you can discover these links. These are now links to Crossref, from DataSite to Crossref DOIs. And you can discover these related or cited literature. You can do it also the other way around, given a paper that was cited in a particular comparison here for the transmission potential of COVID-19 in Iran. You can discover, okay, this paper was used in a ORKG comparison. So the million-dollar question, I think, is can we do what we did for bibliographic metadata or metadata about other entities and assets? And some communities do for specific applications, also for article contents, as we saw in biodiversity, computer science, social science, and so on, for scientific information, but at scale, so efficiently. And I think a main challenge here is how to make fair scientific information production efficient. This is a huge challenge, and at TIB, in the context of the Open Research Knowledge Graph initiative, we are essentially looking at three modalities to address this problem. One is crowdsourced. So I call this the post-publication and then manual approach, where readers or authors, specifically, they can essentially describe their research contributions made in paper in a structured manner. So here, an example for basic reproduction number, or a study on the estimate for basic reproduction number. You can see here at 3.1, you can, of course, describe this value also for its confidence interval. So it's a structured object here. The location, Lombardy, Italy, can be linked to geonames to make this data interoperable. The time period, again, is a structured object with a beginning and end. Dates, and we can also assign a research problem, like the determination of COVID-19 basic reproduction number. So this is great because it's accurate. So humans, experts generally, when they read the paper, they can accurately extract the information and ingest it in this manner into ORKG. But it's, of course, since it's a manual approach, it doesn't scale very well. As you can imagine, we also try to automate this process. So in the post-publication, we can also think of using like NLP models or information extraction approaches to try to automate this task. And here you can see how NLP models can try to, given a title and abstract, potentially also the full text, they can try to suggest certain properties that you might want to use in research contribution descriptions. That's great because indeed it is efficient in the sense that it's automated, and you can potentially scale this approach to the million of articles out there. But unfortunately, the approaches aren't very accurate yet, in particular on the extraction of highly complex objects, information objects, like they have a lot of or multiple relations. The performance of this automated extraction is usually very low. So you always need an expert or the human in the loop, again, that ensures the quality. So another approach is pre-publication. So in contrast to the two post-publication approaches, this one is a little bit different in the sense that it binds into the data analysis step in the research data life cycle. And it ensures that information is created fair at birth. So when it's essentially produced in, for instance, R or Python data analysis scripts, as I'm showing here, you are executing here or fitting a linear mixed model to some data. So you can describe this activity. So here, for instance, the Linux mixed model has an input data set. A particular statistical model is described here, and also the output data set. And the interesting thing here is that you can basically pass variables that you anyway have in your script as you compute these values directly to the step that ensures this information is machine readable. And then you eventually serialize this into a file so it stays in the environment of the user, of the researchers conducting this analysis. And then it can be submitted as supplementary material to the publisher together with the manuscript into the review process. Here I'm using Copernicus publication as an example of an open access publisher. And so these assets, they all flow into the review process. The manuscript is reviewed. In principle, you can also review this supplementary material, but in the end, the publisher would essentially ensure then that the article is in the metadata of the DOI, is linked is supplemented by links to the JSON documents, JSON data that we have here as supplementary material, describing some of the information in the article also in structured form. And you might guess what happens if you do that. Now that we have a published article with its DOI, we can use this DOI and simply harvest the machine readable description of some of the information in the article into a system like ORKG. And if we do this, you can see here for a paper, the two research contributions that are described, so the linear mixed models that were executed here. You have the input data set, that's a larger data set, which is not part of the article itself. So we simply link to it onto, for instance, it's an auto repository. We have an input model for the linear mixed model. This is described, in particular, the response and predictor variables, but also the output data set. That's actually a table in the original article, as shown here. But here now the data is really ingested into ORKG, so we can very easily reuse this data, for instance, again, in computational environments using like Python or R. And load this data again into a data frame so that we can reuse it very efficiently. And also, for instance, in a systematic review that takes such data from a number of publications to power some meta-analysis. So some takeaways, I think scientific information can be expressed so that it is more machine readable than it is currently. I think this is essential for improving the reusability of scientific information, which, given the speed of science and the need of scientific information digested also in various forms at various abstraction levels, for instance, for policymakers, given the speed of the need of this information in current knowledge societies to address our challenges. It's really important to make all of this more efficient than it is currently. Some disciplines have indeed developed their own systems, as I showed you, for biodiversity, social science. There are a number of examples how this can look like, and what can you do once you have information in a database. And they support very interesting tailored applications. But all this is not really general praxis. As you know, we publish in general pretty much exclusively information as PDF or maybe HTML documents. And yeah, so the question is, how do we realize this vision, and how do we move from prototypes to real systems that are used at scale? And this is indeed not exactly a trivial undertaking. In particular, I think the fair scientific information production. So the question, how do we do that efficiently, is really a key challenge, and one that relies also on shifts in practices. So, for instance, in the pre-publication modality that I showed you, it's of course required that researchers are aware of this possibility of these mechanisms and integrate this into the data analysis phase. So that's a change that needs to happen, a shift that needs to, in practice, that needs to happen. And also think that it relies on infrastructure, on changing the current infrastructure that we have, so that all this becomes as easy as possible. So thank you very much for listening, and I hope you enjoy this conference.